if you say given A prove C and you don't give B, that's garbage. Well, whatever.
But you should give some opportunities for
There is
the
no
students who want to
opportunity
try.
to try what, the garbage problem? And you know, the sad thing is, I tell the particular TA, this is 10 problems. I want you to read them and pick up one or two and make the homework. And he just doesn't even bother to read them because he doesn't understand them. So he writes his own that don't make any sense. You change location to confuse me, that's the idea, right? I know, you need electricity. All right, is the light on?
Yes.
Yep, all right. I haven't planned anything specific, so what I did is, in part of reviewing the course, I just cut it and pasted some of the slides in some of the, I don't know, lecture, I think, 10 to 14 or so. So we're not going to review anything about Monte Carlo methods because that was on the latest part of the course, so hopefully they make sense. So we're just going to review some of the earlier things that they are very important, and maybe when we covered them at the early time, they were not making a lot of sense. So let me repeat a little bit about the exponential family, so we can do the regression problem. So this is the general family of these exponential family distributions, and eta is what we call the natural parameters of the distribution. What, you know, this thing looks a little bit weird. It looks different from normal because usually the distributions you see in practice are written in terms of moments, like mean, variance, but there's no mean and variance here. It's all expressed in terms of this parameter theta, but as we discussed last time, there's one-to-one relation between this parameterization and the moment parameterization. We define a few more different forms of this equation on the top by introducing alpha to be minus the log of g. So if you put this inside, you get minus a of eta inside the exponential, and we define the normalization factor 1 over g, and so a is minus log of g, which is log of zeta. Okay, so you can write this in various different forms. This is most probably a common form as well, but they're all the same. All right, so we basically we assume that we have, the reason we use the exponential family is because, you know, with one sort of set of equations, we can model many, many distributions, and in particular, if we do Bayesian inference and the likelihood fits in the form of the exponential distribution, and we use a prior from the exponential family, so a conjugate prior, then the posterior is also in the exponential family. And so we just indicated on Tuesday if the likelihood looks like this, okay? And we use a prior that follows a similar form that I'm writing it here. All the subscripts 0 indicate prior. Then we can, if we multiply the two things together, and we assume that we have a number of data points x1 to xn, we can write the posterior also in the exponential family, where the only thing we do in the exponential family, because it's a conjugate prior, we have to update the coefficients nu n and tau n from the prior values to the posterior values. So actually, if you look carefully at these equations, they're extremely appealing, and they even give physical meaning to the prior, to the concept of prior measurements. So when you look in here, this is the sample mean, and you have n measurements basically with this strength. So you can see the prior as having n0 prior measurements of this strength. That's why there's always people assign physical meaning to the prior variables, and that can only happen in the exponential family. Okay, and the other thing that it's very significant, if you want to calculate the predicted distribution, there is a very closed form solution, and it's basically the normalization factors of this exponential family distribution is the ratio of two normalizing factors times this factor that depends on the data set. So if you are going to do model selection or model comparison, effectively the formulas for the normalization factors that you need when you do Bayesian inference are there, and if you want to do prediction, like in this formula, everything fits in a very nice closed form solution. Now, something that fits in a closed form solution doesn't mean it's the best solution, right? We only use it because it makes things easy. So it doesn't mean necessarily it's the best, so I'm not trying to advocate it's the best, but I would say from all the family of distributions, most probably this is the most widely used. Okay? All right, and we proved in early lectures, and we mentioned this on Tuesday, if you want to compute the expectation of u of x, so if you, let's say, the sufficient statistics is x, so if you want to compute the expectation of x, which is the first moment, you can do this by taking the gradient of a with respect to eta. So remember, a is the log of the partition function, so there, this is not an easy calculation, but if you know a and you take the gradient with respect to eta, then this is the first moment. And similarly, you can show the covariance is the second derivative, is the Hessian, etc., etc. And more importantly, from the last equation, we can conclude that this is positive, which means that the function a of eta is a convex function, because the covariance is positive. And what that means, so if I write the exact mean equal to the gradient of a, okay, because a is a convex function, I can invert, and from mu go to eta, and from eta go to mu. This is very important, okay? So the mapping from this natural parameterization, the parameter theta to moments, is invertible. So if you write me down a distribution, a Gaussian, in terms of moments, I can write an equivalent form in terms of natural parameter theta. And in the early lectures, we gave this one-to-one mapping for various distributions, for sure, including the Gaussian. Okay? All right. So let's, there was a regression example that we did before we even formally talked about simple regression problems. So I think it would be a good reason now to revisit that example and see how we can treat, we can write down models for regression using the exponential family of distributions. So you remember that when you do regression, right, you have some data x and some data y, the response, and y is noisy. And then effectively the regression function is something that looks like this, and it represents the mean response at every location x. You remember, what we do it in a regression at each location x, we don't say, oh, y is equal to that value. We fit a distribution, all right? And here, we take the mean of that distribution to be a function f of theta transpose x, where theta are some parameters to be computed, the regression coefficients, okay? So, so schematically, if you give me x and I know theta, I define xi, that is theta transpose x, and then the mean, right, this is mu, the mean is f of xi, okay? Now, remember, if I make this distribution to be part of the exponential family, there is one-to-one mapping between the mean, mu, and the natural coefficient theta. Okay? And that function is, we call it here psi. Okay? And it is an invertible function. So if you have a particular distribution from the exponential family, psi is very given. Okay? You don't play with it. Psi is given, let's say, for the Gaussian. But right now, f can be anything you want to. I mean, when you write the regression models, the regression function can be anything you want to. So we would like to see, can we make a choice of f that somehow makes this whole regression model easy? And the answer is the canonical response choice, which looks like this. So we're going to select that xi, you remember xi is theta transpose x, right? This is how we define regression models. Xi is theta transpose x. We're going to make xi equal to eta, which means if you look at the m from the left, m is a function of xi, and because xi is equal to eta, this is also psi minus 1 of eta. You see that? So basically you have both of these relations to apply. So the function f that we choose here, it's not an arbitrary function, but is the inverse function psi that maps the mean to the natural parameterization. Okay? So basically the idea is I can use anything for the regression function, but I choose to use psi minus 1. And by using psi minus 1, I make xi and eta to be one and the same. Okay? Now you may say why, because you will see somehow things become extremely simple and very appealing sort of from implementation mathematical point of view. So again, at every given location x, right, the mean response mu is a function of xi, and we choose that function to be the inverse of psi. And what is psi? For a given exponential family is a mapping from the mean to the natural parameter theta. All right, so this slide, when we used it, it was extremely heavy. Maybe it wasn't making sense at the time at all. Maybe it will not make sense today as well. But let's try to see if we can discover what is going on here. So we are going to assume, because it's a regression problem, that we know the input and output. So x, I have it as a volt because it's a vector, some high dimensional input. Let's say the output is a scalar. I denote this y from I equal 1 to n. So what I do is I write the log likelihood, okay? And remember, this is, we assume that we are playing with the exponential distribution, so the log likelihood looks like this. Does this look familiar to you? From where do I get this? If you remove the logs, what do you get? You will get h times the exponential of what we had. Eta times what? The sufficient statistics, and for each point, really, the sufficient statistics is the yi. Right? That's the information we have. So this is, or yn as I indicate here, minus a, defined it at the natural parameters eta n. You remember the exponential family? Which form am I using here? Or maybe without a theta. How about this form? All right? So we are basically taking the log of that, so we're going to have the log of h, and then eta transpose u minus a of eta, and u is basically y in our problem for each data point, and we have n data points. Okay? So basically the log likelihood looks like that. Okay? A summation of the logs of h at yn plus eta n times yn minus a of eta n. Okay? So, let me see so we don't have to do all the details. So we are rewriting this, okay? So what have I done from here to there? What have I done to go from here to here? What did we say when we do the canonical choice for the function f? That xi and eta are the same thing. So the parameters theta here are the same as the parameters xi, and what are the parameters xi? Theta transpose xn. You see that? So theta transpose xn minus the summation of a eta n. So right now, let's not bother to do any Bayesian analysis. We're going to do a maximum likelihood estimation, but you can extrapolate that doing a Bayesian analysis will also be very straightforward. So what we're going to do is we're going to calculate the maximum likelihood estimate for the parameters theta. So to do this, we're going to have to take the derivatives of this with respect to theta and set them equal to 0. So let's see what we get. There is no theta here, so no derivative. Here what we get is xn times yn, and I see that here, xn yn. You see that? All right? Xn yn. And then we have the derivative of this with respect to theta. So to differentiate this with respect to theta, you have to take derivatives with respect to eta. And what's the derivative of a with respect to eta? From the properties of the exponential family? What is the derivative of a with respect to eta? You remember we said is the moment m? Yes? And then we have the derivative of theta with respect to theta, but eta is the same as xi, and xi is theta transpose x, so you get an x. So the gradient of the log likelihood is basically summation over data points of yn minus mu n times xn. Okay? Now, this form that you see there, all right, where for every data point the gradient is driven, you notice, by the error. All right? Because in essence, yn, what is it? Is the data point that I gave you, the nth data point, and what is mu n is the mean of the regression function. So that error is that drives the calculation of the parameters theta. So this form is almost universal in many, many problems in machine learning. This is how you get it. Okay? And I will show to you shortly, in most of the times, in most of the algorithms, you don't actually use all the data points all together. So you actually do the updates of the parameters one data point at a time, which means you really compute the gradient as only this term here. So then you update the parameters, you go to the next data point, you update the parameters, etc. So in a matrix form, if you put all your data x together, this is x transpose y minus mu, where y is the vector of all the yi's, and mu the corresponding mean in your regression function. You can, what you can do is actually, you can take further derivatives of this and calculate the Gaussian, which is the second derivative of the log likelihood, all right? And if it is basically straightforward, the calculation, there is nothing there, so I'm gonna, here is the formula. So if you take second derivatives, what you get is minus x transpose wx, where w is a diagonal matrix that involves these terms in the diagonal, okay? So there is a universal sort of algorithm for this type of problems, that it's a derivative of the Newton algorithm for doing optimization and computing the parameters. So basically, what the Newton algorithm says, the update of the parameters involves here minus the Gaussian inverse, all right, times the gradient. If you have never used the Newton's algorithm, right, it's sort of one of the most basic algorithms for doing optimization. And again, the way you update the parameters is theta t plus 1 equal theta t minus the inverse of the Gaussian. All right, so the Gaussian is like that. Minus will cancel this. So the inverse of the Gaussian times the gradient, which x transpose y minus m. Okay. This is a very, very fundamental algorithm, again, in machine learning, not just in the context of regression, but classification and many, many other tasks. So there is a merit to actually know this type of updates. So if you rewrite basically this algorithm, right, you plug in things, etc., what you do is you get what is called iterative reweighted least squares. It looks like a least squares problem, all right? But you know this is a weighted least squares because this matrix W is updated at each iteration. So literally you get a least squares problem, but with weights that need to be updated at each iteration. All right. Now, if you want to apply this algorithm online, one data point at a time, rather than using all the data points, the algorithm actually takes this extremely trivial form, one line. All right? So this is the predictive, the mean of the regression function at the iteration n. So this is the error that you do. You remember I told you always the gradient comes like this. And rho is what is called a learning coefficient. So this algorithm is really a stochastic gradient descent algorithm. And it is basically the same gradient descent algorithm that you use in training neural networks, in deep learning and everywhere else. It's really universal in machine learning, okay? The only thing that is going to change is a little bit this form, depending if it is a regression problem, a classification problem, but more or less the update looks like this. You don't have to take all the data points together. You operate them one data point at a time, and it's amazing that this algorithm works. All right, there are not many proofs on why it works, but well, maybe for this particular problem, for the regression, because it's the mathematics are more clear, maybe there are proofs, but in general, using this stochastic optimization works. And it's actually the only way that you can update parameters in complex networks. Really, we don't know any better. Okay? So I want you to remember that stochastic gradient descent looks like this. And effectively, it is sort of an online implementation of the Newton's algorithm for this type of problems. And for the exponential family, it certainly looks very simple. All right. Any questions with this? So this is way more general than, so there's lots of elements that are very general in training systems, complex systems, and updating parameters as you collect data. Okay. All right, let's see what we have here. I think so in the following lecture, we discuss a lot about the partition of Gaussians. That's a very fundamental problem, not only for the things we did this semester, but for those who will take the course next semester and where we will discuss about Gaussian processes, you will see the idea is practically the same. Okay, so the idea here was if we have a multivariate Gaussian and we split X in two parts, can we conveniently write the marginal distributions and conditional distributions in terms of the information that we provide in mu and sigma? And the answer is yes. So what we did is we partitioned the mean, we partitioned the covariance matrix like that. We did the same thing with the precision matrix, we partitioned it like that. And remember, when you invert things, be sure, because you partition it here, on how you connect this lambda with this sigma, okay? So you have to do some algebra to do that. Just in summary, some of the results, whatever I see, the conditional comes to look like this, okay? So it is still a Gaussian with this mean, and this mean, when you condition on XB, the mean comes to be linear in XB, okay? And if you write this in terms of the precision, it's really very easy because it's lambda alpha alpha inverse. Okay, so in terms of the precision, this term is very simple. I mean, you say again, where do we use this? Where was it useful in the class? Very easy, you know. Imagine you have all this variable x, you know that the big X follows a Gaussian distribution, and now I give you some measurements. Using this formula immediately, you can compute the distribution of the other variables. All right, and when we do Gaussian processes effectively, these are the type of calculations we will do, and they will look like this. The only difference is, you know, sort of we will apply this over function spaces rather than matrices and vectors. But the equations will look literally identical. We discussed about the this partition formula for inversion of covariance matrices and precision matrices. And let me see if I can give you a few of the results. So this is an extremely important result that we came with from playing with the inversion of these matrices. And this is follows under the name Selman-Morrison-Woodbury formula, okay? And it is a formula that allows you to invert, let's say if you have data points of dimensionality d that is small, and the number of data points is very large. So sometimes when you calculate the covariance matrix, let's say it comes to be of some form like that, it's an n by n matrix, but using this Woodbury formula, you can actually only invert a d by d matrix. Right, so rather than inverting, let's say, 10,000 by 10,000, you invert something that is 100 by 100, okay? And this is fundamental to this Woodbury formula. And there are sort of various different versions of this, including also this formula with determinants that is you see here. This is a formula that I would say is most probably the most common use, you know, formula in, from linear algebra in the context of machine learning. It comes everywhere, okay? So everywhere. So you know, if your somehow your problem can fit in this form, you should always wonder: do I really have to invert this, or maybe the Woodbury lemma will allow me to do some trick and invert a lower dimensional matrix? And I think I give you here one example. If you let's say you have a covariance matrix that is n by n, and somehow now you collect new data points defined by the matrix X, and you have to invert this, you can show actually directly by changing the symbols on the Woodbury formula that the only thing you need to do is invert a d by d matrix. So imagine if n is again 10,000 and d is 10, your choice. Do you go and invert 10,000? And I can imagine, you know, thousands of students, they go and they invert 10,000, they realize their computer cannot do it, but this Woodbury formula allows you to do this type of calculations. And I think this is another sort of, if you, you can see here, if you, before we edit a bunch of data through this matrix X, but you know, if you think the simplest case of this would be if X is a vector and we have something like that, which is what is called rank 1 update, and you can see in that case actually the inversion is practically analytical. You know, if you want to add only this U and V transpose there to invert the left hand side, effectively you don't have to do anything, it only involves A minus 1. Okay? So very, very nice formula, and again, extremely common formulas in the context of Gaussian processes. I mean, certainly, if somebody tells you what's the Woodbury formula, you don't have to remember it. You have to remember what it does, and if you look, you know, if you have a computer in front of you, go to Wikipedia and say Woodbury formula, and if it doesn't come immediately, then we have a problem. Okay? I doubt it. Did it come? No. Okay. All right. And this is, you know, if you want marginals, the marginals usually are very nice in terms of covariance, because the only thing you have to do is, if you want a marginal of XA, is the mean mu A and sigma A. So it's in terms of the partition of the covariance matrix, that's very easy. Okay. I'm only going to put this up in as a reminder, because we did not really, we use it, it was there. To which extent we elaborated, it's maybe in future courses, but we defined very many different types of non-informative priors. The idea of non-informative priors is, right, if we don't really know anything, what can we do? And the idea is we're going to use non-informative priors, and the most fundamental non-informative priors are the ones that are derived from Jeffreys formula and what's called Fisher information. So basically, the pi of theta is the determinant of the Fisher information square root, where the Fisher information is defined from the Hessian of the log likelihood. Okay. If you read a little bit more about information theory, you will understand from where this thing is coming, but more or less, this is the formula for Jeffreys non-informative priors. And if you apply it to simple problems, so for example, if you try to compute the Jeffreys non-informative prior for the mean of a Gaussian, it comes that prior is the uniform prior, right? That's, yeah, completely uninformative. Very nice. And if you try to do the same thing for the variance, all right, so if the variance is unknown, then using the Jeffreys prior, it comes out that the non-informative Jeffreys prior for the variance is 1 over sigma squared. And those things you need to remember, right? For the mean, if you don't want to constrain anything, it's a uniform distribution. The prior for sigma squared, it's always 1 over sigma squared. Okay? And we have extensively used this when we try to do inference in the context of univariate and multivariate Gaussian distributions. Okay, so then we move, we talked about different priors, but then, we move to the context of hierarchical prior models. And let's say before we had the parameters theta, and so when we express the posterior, it was the likelihood times the prior. But right now, let's assume that the parameters theta depend on some other parameters. So when we postulate a prior model for theta, there are parameters coming in that prior model that you don't know. So effectively, not only you have theta, but you have these new parameters phi, from which theta depends on. And so when you try to compute the posterior, really you have to compute the posterior of theta and phi, given the data, and that is the likelihood model. All right, and because phi is contained in theta, so the likelihood is p of x given theta, times the prior of both parameters theta and phi, which is the same as the prior of theta given phi, times the prior of phi. So this equation that you see here is a typical hierarchical Bayesian model, where for anything you don't know, you put a prior, and you keep going until some point you give up, with the hope that as you keep doing this, the parameters as you go to the right, become less and less important. So for example, if you go and assume, let's say, that the prior is a Gaussian, then you don't know what the mean and the variance is. So you're going to put some distribution on the mean, but that distribution is going to have its own parameters. And those parameters, whatever distribution, say you put a beta distribution, we have their own parameters alpha and beta. And you keep going like that, right? So in this case, what we have is, we have parameters theta, and then theta depends on phi, so a hierarchical model looks like that. So the idea in this hierarchical Bayesian models is how do you select, how do you, this posterior there that you see, as you keep including more parameters, becomes very complicated to compute. So what do you do, what type of calculations can you do to simplify the problem? And let me see if I can, I think we can discuss everything in terms of this table. So how about if you guys look at this different choices and tell me what exactly we do in each choice. So on line 1, what do we have? Say it again. This is an MLE estimate, right? There's only parameters theta, so we write the likelihood, okay, as a function of theta. We take the, we find the argument theta that maximizes the likelihood. That's the MLE estimate theta hat. Okay. What do we do here? I mean, here is basically the likelihood times the prior, and because I plug in an eta there, the implication here is you choose some eta. You say, okay, these hyperparameters have some values, okay? But effectively, this is the anormalized posterior, so you find the map estimate, you find the theta that maximizes the posterior for some eta, okay? So you don't play with it. All right, now we go to the hierarchical Bayes equation. So tell me what exactly is going on here. This is a very important part of Bayesian analysis, what you see on this equation. So, and I am going to remind you that at the end of the day, we're going to compute the complete posterior for the parameters theta, but as this formula indicates, we're not going to include in that posterior the parameter theta. We're going to fix the parameter theta to some value. And according to this empirical Bayes formula, what is that value? Is the value that maximizes what? What is that? I hear lots of things. The marginal likelihood, okay? So basically, you notice here, the parameters theta have been integrated out, okay? And effectively, we have the likelihood as a function of theta only. So the idea here is that if you use a point estimate for the parameters in the hyperparameters, eta, all right, the problem does not overfit, okay? You cannot do this for theta, but you can do this for eta, okay? So what you do is you maximize this marginal likelihood, okay? You fix the parameter theta, and then for this parameter theta, what you do is you actually compute a map estimation, or you do full Bayesian inference for theta, okay? And so this is very similar to the ideas of the evidence approximation that we discussed, right? It's all the same, okay? This is fundamental to Bayesian analysis. Now you can extend this a little bit further, where you have the marginal likelihood, okay, where again theta here has been integrated out, and you put a prior on eta, and then you do a map estimation for the parameter theta. This is what the formula shows. And of course, if you want to do everything perfectly fully Bayesian, then you treat the parameters theta and eta the same way, and you compute the posteriors of both theta and eta together. Okay, that would be very complicated. And actually, if you look in textbooks like Murphy's book in machine learning, he rarely basically does anything that looks like this. In most problems, the parameters are fixed, eta are fixed to some point estimate, all right? And then he goes back even not to even do full Bayesian analysis in terms of theta, but calculate a map estimation for theta. Okay, so this is, it fits under the category of empirical Bayes. So this table here is extremely important, okay? It's extremely important. Now, in a lot of these problems, you notice there is, you have to, they're all optimization problems, all right? And I realize I have no idea if the microphone is picking me up, so I can say anything I want because I forgot to turn the microphone on. Is it on? No, it's the last day, so we'll keep it off for the rest of the day, as the tape obviously will not work. Okay, I put it on just for the history books. What I was saying. So these optimization problems in modern machine learning platforms, you can actually do them with very efficiently. You don't have to program anything from scratch. It would be one-line type of calculations. All right, we talked a little bit about model selection for sure in the context of regression. So if let's say you're going to fit something with polynomials of different order, what is the right order of polynomials so you don't overfit? Because if you're interested to maximize the likelihood, you can use a polynomial of order 1,000 or 10,000, all right? But the idea here is you need to fit the data as good as you can, but also keeping the complexity of the problem at moderate levels. And this leads to ideas of model selection. And let me see if I have a cumulative formula to tell you. I'm going to come back. Okay, this is a good plot to discuss, right? So remind me, what was this beautiful plot? Because this is, again, very fundamental. If you go and give a presentation on, model selection, you're going to be using this plot, basically, because this is the easiest way to communicate the concept. So remind me, what do I see in this plot?
Different model.
So we basically have models of different complexity, and we have on the horizontal axis we have different data sets. All right. So is this a simple model, the M3, or it's a complex model? I mean, when I look at M3, right, is covering a lot of data sets, so it's explaining a lot of data sets. So what type of a model is that?
Complex.
Huh?
Complex.
Complex, and it explains a lot of, if it explains a lot of data, it assigns low probability in its data set. Okay? Then this is a model of intermediate complexity. And this is a model of low complexity. Let's say it explains only a few data, so you can think of a straight line, right? It fits only a few data sets, okay? So the idea here is the correct model for a given set of observations. If you have some data, the correct model is of some intermediate complexity, okay? And so your job is, when you do model selection, not to use a very complex model, so you don't overfit, not to use something very simple, because, for example, in this case, if you have something simple, you won't be able to explain this data set here or there. You know, you only explains a very small sets of data. So if you do a little bit of perturbation in the data, all right, then somehow the whole model will fail to give you to give you an explanation. So the idea here is, again, the key ingredient here is that the way that I plot these probabilities, they are normalized, right? So every distribution is trying to explain the underlying data set. So this is equal to 1, okay? So in this case, the assigned probability is very low. Here in this case, you explain a few data, but the assigned probability is very high. All right, generally speaking, if we have models MI, all right, each model MI has its own parameters theta I. So you can write down the posterior for each set of parameters theta I for the model MI as the likelihood times the prior divided by the normalizing factor. And using this calculation, you can actually write a posterior over models. So the posterior of the model MI given some data X is the likelihood, all right, under model MI times the prior of MI divided by pi of X. So this is an amazing result, right? But we were talking about posterior over parameters. Now we can actually talk about posterior over models. All right? Can you tell me, so looking at this equation, right? How do you calculate the likelihood P of X given MI? Just throw me some equations. How do you calculate the likelihood of the data given a model MI? There are no parameters there, and the only way I know how to calculate likelihoods is when I involve parameters. So how do you calculate pi of X given MI? I mean, when you can write down the likelihood, if you know the parameters, what you need to do is, right, you can write this as P of X comma theta I, and then integrate in theta I. And then you can write this as P of X given theta I inside the integral, which is the likelihood that you know how to handle, like this likelihood there, times the prior of theta I, integration of theta I out. Right? So if you don't see parameters, it's nothing difficult, right? You plug them in and you use the marginalization rule to get rid of them, okay? So this is an integral that involves integration of the parameters of the model theta I. This is a prior of every model. Let's say every model is equivalent. So if you have 5 models, maybe it's 1/5. And pi of X is basically the summation of all of these things over all the models, okay? The idea here is, again, we have managed in a Bayesian setting to compute a posterior over models. So in principle, if you have many alternative models, a way to compare things is to compute the posterior. So the model has the highest posterior is the best model. Now, nobody does this because this is very computationally expensive, right? So if you have 100 models and you try to do this calculation, it's way very expensive. Okay, nobody's going to do this in practice. But people, what they do is they actually compare 2 models. So if you give me 2 models, what I can do is I can take the ratio of the posteriors and I can write this as the ratio of these likelihoods times the priors. And as I just discussed it, I didn't realize that the formula is given here. These likelihoods are integrated, are looking like that with integration of the parameters out. And this is the ratio of the priors. And this ratio here is what we call the Bayes factor. You remember that? So multiple ways to actually compute, to compare models, all right? And certainly, the Bayes factor is a very easy way to compare 2 models. I mean, if you know the likelihood of each model, if you know the prior of the parameters of each model, you can easily compute this. And a nice way to compute it is with Monte Carlo integration. So the ratio of the 2. So if you calculate this and it comes that it's way greater than 1, then you say the model M1 is more, the most possible model. There's a much higher posterior, and so you select model M1 to do your analysis. Now, when you write these formulas, keep in mind that you see an extreme dependence on the priors. So somehow, you can get very many different results if you put some priors that point towards one model or another. So if these are not uninformed, okay, you will get basically whatever results your priors tell you, unless you have very strong evidence from data. And there is an extremely simple, actually, MATLAB program that I gave you that tests this model selection for regression problems. And so this is my simple model M1, the medium complexity model M2, and some M3 where it fits perfectly the data, but you actually cannot do any predictions with. And so when you calculate the posterior of the models for a given data set, you can see that in this case, for this particular example, I read the number here 1, that the straight line is actually the best model for that particular data set. Okay? There is another example here, but you see that the quadratic is the best model. All right? Look at the posterior, how big it looks, and the rest basically very, very small. And indeed, you can see the data set fits very well with a quadratic. And again, this is evidence for a given model. The marginal likelihood looks like this, and effectively is the most important. If you're going to compare one model with another, the only thing you can do is use the data, and the only entity in a Bayesian setting that contains information about the data is this marginal likelihood. So effectively, what you need to do is, if you do model selection, you need to be able to compute analytically for your problem the marginal likelihood, all right? And then somehow find the model that has the maximum marginal likelihood, that best explains the data. And I remind you this, we discussed this on Tuesday. The calculation of the marginal likelihood, which is the normalization factor in Bayes' rule, it's nothing else but a ratio of normalization factors for the posterior, the prior, and the likelihood. You remember this, right? I mean, we have done this in different problems, but if you look at the different terms on the left and the right, they contain functions of theta and some normalizing factors, some coefficients. So if you cancel everything that depends on theta, what you're left to do with is that the marginal likelihood is basically a normalization factor for the Zn, I suppose here, is a normalization factor. Where is Zn coming? A normalization factor for the posterior, right? A normalization factor for the prior, and then you have a normalization factor coming from the likelihood. Okay? And it doesn't matter what distributions you have. I mean, if somehow these distributions, they are known, okay? For all distributions, we know the normalization factor, so this is something you can write down very easily. So in the literature, you will see lots of papers that basically give you some very complicated forms for this log likelihood, and you'll be wondering from where that thing comes. Well, it comes from this formula. And if you see complicated things with gamma functions and to some power, etc., well, no big deal, because depending what distributions you have, these normalization factors are complicated. But for each distribution, you go to Wikipedia, and you say, what's the normalization factor for Gaussian-Wishart, let's say, distributions? Is there it is. So you plug it in, and you're in business. Okay, and just one slide here on, for example, if the prior is a beta distribution, the likelihood is a multinomial, a binomial distribution, then you can actually write the normalization factor P of D to be this nice formula. Okay. Now, if you attempt to, let's say, so I see in this formula, right? There are lots of hyperparameters like alpha and beta from the prior. So really, if you want to select, if you want to do Bayesian analysis and you want to find the best parameters alpha and beta, the only way you can use is to maximize this likelihood with respect to the parameters alpha and beta. And that looks a trivial optimization problem, but depending on what functions you have there and the expressions, it may not be as simple, and there's no guarantee that there is a unique, basically optimal set of parameters, so you have many local minima that you can use. So there is a lot of literature here for different type of distributions on how you calculate this how you do evidence, basically approximation. And just again, to show you if the likelihood is Gaussian, all right, and the prior for the mean and the covariance or precision is actually Gaussian-Wishart model, all right? So actually using this formula and plugging in the normalization factors, you get this wonderful formula, all right, for the evidence, all right? And so whatever parameters you have, actually, you can compute them by optimizing this expression. And it looks simple, it looks very elegant expression, but these are matrices and determinants, and these are multivariate gamma functions. So it's not something actually you can do by hand, okay? But certainly, with symbolic programming, maybe you can get some approximations with this type of equations. All right. Another thing we learned that is very, very fundamental to Bayesian analysis is Laplace approximation. So remind me, what is it? Very, very fundamental. It's like when you try to do Bayesian inference and you have many parameters, that's sort of the first approximation you should do to see how things look like. So what's the Laplace approximation? What's the idea? We approximate what? What do we approximate with the Laplace approximation? Don't read the slide because maybe it's out of content. The formula, maybe it's useful, but tell me, what do we approximate with the Laplace approximation? The posterior of the parameters, right? And we approximate the posterior of the parameters that can be a very complicated distribution with what? With a Gaussian. And you don't need to remember formulas. What do you do? How do you fit that Gaussian? You basically fit that Gaussian in the mode of the posterior. And so you need to know the mode of the posterior. And then what you need to know is you need to know the curvature of that Gaussian. And the curvature that you use, you compute it through the second derivative, basically, of this log posterior, okay? So effectively, an approximation looks like Gaussian. It's centered around the map estimate, and the precision, basically, is defined by the second derivative of the log posterior. If you use this Laplace approximation, so this has many, many uses, right? So if you want to do Bayesian inference, and this is something complicated, you fit the Laplace approximation, and you sample, let's say, from a Gaussian, rather than sampling from a complicated distribution. So, but this will not work, let's say, if your distribution has two modes. If you have two modes, how can you fit a Gaussian that has one mode? So you have to be very careful. But if you have a single mode, and usually you have a single mode, if you have lots of data, right? The posterior becomes sharp, and the Laplace approximation becomes very accurate. Okay, so it becomes a very good approximation. But again, if you have multimodal distributions, that's another story. So you can actually use this Laplace approximation to compute to do model selection, and somewhere I am not going to go through the derivation. You can we have already done it. For a particular model MM, you can show that you know, the evidence, the log evidence, if you like, is given by this wonderful formula. Okay, and you remember we said we are actually, you know, when we do, you know, when we do model selection, basically, we're going to have to maximize, if you like, the likelihood, but penalize basically complex models. And you notice, if you look carefully at all the terms here, there is a minus term there that controls the model complexity. And you can simplify this equation, and you can show that in the limit of many, many data, the log evidence becomes basically the log evidence for parameters fixed at the map estimate minus the number of parameters divided by 2 times log of n. So this term here is fundamental to controlling complex models, because if you try to maximize this, it will maximize this term, but there's a minus sign there, is going to try to keep the complexity of the model low as well. Okay? And so this, you know, goes well with the Bayesian information criterion, and again, you know, if you do different sort of approximations, you get something that looks like this. Some form of a likelihood term here, minus some penalization term that controls how complex the model is. And that's practically standard in all Bayesian settings. And there is an example in the notes that is using this for regression and different versions of this model. And so I'm not going to go through this. So when we discuss about Bayes factor for model selection, different statistics communities give you different values on, remember the Bayes factors is like model 1 over model 2, right? So you can, or in this case, I think when you see Bayes factor 1, 0, it compares model 1 with model 0. So when this is less than 100, you select M0, less than 1/10, you have strong evidence for M0. So basically the statisticians are extremely conservative. You need, you know, if the Bayes factor comes to 1.1, they tell you, sorry, I cannot do anything for you, okay? The evidence has to be very strong. So, you know, you have strong evidence for M1, the Bayes factor has to be greater than 10. Okay, so be careful not to simply say, oh, this is greater than 1, so model 1 is the best. The statistician will tell you, no, sorry, you better be greater than 10. And if you really want to have a decisive evidence for model M1, if I can read it here, it says the Bayes factor greater than 100. Good luck with that. All right. I don't really have time to do any of the above. We really, when we did regression, right, we showed that doing maximum likelihood, it's least squares, doing a map estimates, regularized least squares, and also we discussed some online updates of the regression coefficients, and since by clicking randomly here, I come up with this equation, And hopefully this equation looks to you the same as what I started the lecture today, does it? Remember this? Right, this is the mean of the regression function. This is your data Tn, and this is the function phi of x. Remember I said for stochastic optimization, you do something like that. Comes from the gradient, of the this error function here, okay? And eta is a learning rate, and this is the stochastic optimization algorithm. This actually, again, it's amazing. One data point at a time, and it works. So it's not like you're going to throw thousands of data together, invert matrices. No, you're going to do this one data point at a time, and it's very possible this algorithm will converge before you even bother to consider all of your data, right? So you will consider part of, of your data, and you may find your convergence answers. We may do this next semester, depending on how I feel. But we mentioned that when we use Gaussians to do Bayesian regression, the formulation is it's a little bit sensitive to outliers. So you may want to do instead of L2, you may want to do L1 optimization. And there are various algorithms that account for that. And the most popular algorithm is the lasso algorithm. If you check again on Wikipedia, you will find more than 1 million citations of the lasso algorithm that basically, rather than minimizing the square error, it minimizes the absolute error in the context of maximum likelihood, and it comes to be very robust to outliers, and there are several sort of ways to reach that point. So anyways, in a Bayesian setting, we computed the posterior of the parameters for a very trivial case. We computed a predicted distribution. Okay, so we put some prior, obviously, on the weights. We took them to be a Gaussian. And the implementation was quite nice. You can see it here on action. You have no data yet. So these are contours of the prior. So samples from the prior for the parameters, you get all these weird straight lines all over the space. As soon as you provide one data point, all the samples for the weights basically give you lines that pass close to this point. And you notice now the posterior becomes more focused. And as you get more points and more points and more points, the posterior basically converges to a point, and you get solutions that look like nicely, they look like that. The reason you need to sort of review this type of equations is because later, if you want to learn about Gaussian processes will have a very similar form, but a little bit more complicated structure. But you need to have an appreciation of this type of equation. So for here, if you train the model with data bold x and bold t, and now after you train and you compute the posterior of w, you ask, at any given point x, can you tell me what is the probability of the response? Well, it comes to be a Gaussian, all right? So this is the mean and this is the variance. And interestingly enough, you can see that the variance changes with the location, okay? There is a nice structure here that somehow we mentioned. You can also write it in terms of kernels. And if you want to look at this with schematics, if you have one data point, all right, the predicted distribution has very high uncertainty away from that data point, all right? So you can see this is your data point. That's where the uncertainty in the predictions is the smallest. Away is very high. If you had two data points, the uncertainty again away from the 2 points is very high, but close to the 2 points, So somewhere where you do sort of interpolation, if you think like the uncertainty, it's reasonable. If you keep adding more points, you get error bars for the predicted distribution that looks like that. This is the generating function for the data, and I can guess that this is the posterior mean for the predicted distribution. So the results actually, when you do Gaussian processes, they look very much like that, okay? But keep in mind, right, in the context, when you take a statistics course, you don't take a statistics course to do fitting something like this in 1 or 2 dimensions. You should not hesitate to actually do this thing in 100 dimensions. I mean, I remember, I was recently, a month ago, in the PhD exam of a student of another professor in civil engineering, and to my surprise, they were using very complicated codes to generate data, and then when it came to Bayesian inference, they were doing something in 1 dimension. And I was so excited to see something in 100 dimensions with all the fluid flow and the mechanics. And it's like, why are you not doing this? Because yes, we can. I mean, we're showing this schematically just for demonstration purposes, but you can do this in 100 dimensions. As a matter of fact, the state of the art is maybe 1,000 dimensions. And if you don't know, you say, I'm limited, I can only do something like this in 1 dimension. But if you know a little bit, you realize you can actually do this in very high dimensions with many variables, where commercial software will not do it, but if you search and find research software, you will be able to do this in 500 dimensions. And of course, in 500 dimensions, you may say, do I need 1 million points to do all of this? Well, and that's where ideas of design of experiments and other nice things come to play a role, and so you will need to learn a few of those things. All right, so this is nice results. Okay, all of these lines that you see are basically samples of the parameters from the posterior, and for each sample you plot the regression functions. So this is a good way to solve the variability in your model, all right? But if somehow you average and you only look at the mean prediction, the mean prediction looks always very nice, but these samples are very important because it allows you to actually figure out how the response here correlates with the response somewhere else, and you can actually compute that analytically. And obviously, these functions that we use for regression, they were of local support. And if you are away from those functions in your data, basically the predictive uncertainty, it's controlled by the noise in your model, and there is no way you can reduce this below that point regardless of what you do, okay? So, and again, there is generalization of all of these things in the context of Gaussian processes, and for those who may get excited because they were told that life is all about Gaussian processes are not anymore the state of the art in doing this type of problems. But still, we will spend a third of the course next semester to discuss about Gaussian processes because they are sort of standard models for doing regression and many other statistical tasks that are of interest to us. All right, 1:44, I'm going to stop there. So try to submit the remaining homework problems by Monday, okay? My apologies for the cancellation of the problems and the quality of the homework. That's as much as I can say. But you have to remember the quality of what you learn and the assistance you get, it depends on all of us. And some of you are going to be TAs in my class next year, for example, and the quality of your TAing will affect the class. If all of us, don't, do this properly, we're going to be getting homework assignments that make no sense. Okay? All right, so happy holidays, happy New Year, happy Nicholas Day, which is today. I can celebrate my name day, all right? And I will see you around.
I hear that you
Yeah, I'm not going to be here Monday and Tuesday, but I'm going to be here
Wednesday
today and tomorrow.
tomorrow.
Yeah.
I want to write a proposal to you about the money scale, but I don't really understand.
I'm going to send you an update also of the in-house paper because
I know. He will send me his paper.
yeah, he's trying to finish it this week. So, yeah. But if you want, we can meet tomorrow.
Tomorrow?
Yeah. You're not going to be ready?
No, I haven't write a
All right.
proposal.
Okay. So send me when you finish writing, and we'll meet on Wednesday when I come back.
Next month, Wednesday?
Yeah.
Okay.
Yeah. But send it to me so before we meet,
Yeah.
you know, I can
No, I
read
know.
it and know something about it.
And I think I don't really understand the motivation about the multi-scale in the decoder.
Yeah.
I know why you. I know that encode decoder is a standard select in the thin version,
Yeah.
but I don't really understand why